This is going to be the talk by Raymond Shen from Keysight, and he's talking about a test bed for 6G non-terrestrial network. So a few words about Raymond. So Raymond Shen is a PhD. He's director of the 5G, 6G cyber government solutions at Keysight Technologies. In this role, he leads Keysight's vast portfolio of end-to-end 5G and 6G test and security solutions for defense and government. He also leads Keysight's cybersecurity and spectrum monitoring solution, managing solutions that include handheld, outdoor, and modular platforms. He has over 24 years of experience in spectrum monitoring, wireless signals, and security, with particular expertise in cellular signals. Shen has a BS from electrical engineering from Caltech and a Master's of Science and PhD in electrical engineering from Stanford University, where his PhD thesis was in the area of neural networks. So we are pleased to have Raymond. Oh, Raymond, here you are.
Thank you so much, Ashutosh, and thank you all for your time here. Today I'm going to go a little bit deeper into one particular subject area, which is non-terrestrial networks for 6G. And in particular, I'm going to talk about test beds for prototyping, sandboxing, research and development. Before I get there, I remember the days, actually not too long ago, maybe just a few years ago, when every 5G presentation had the triangle, the obligatory triangle with the use cases, and after the first 10 times you could recite EMBB, URLC, and MMTC. So I don't quite have that hexagon yet for 6G, but I thought I would talk a little bit about 6G. So we see 6G enabling new use models like holographic and multi-sensory communications, like touch and smell, not just sight, and all-inclusive social Internet of Things, as well as human-to-human and human-to-machine networks, and also widespread use of digital twins, sort of going in between the digital domain and the physical world as well. So 6G will eliminate physical and temporal distance between people through holographic imaging, and networks will be powered by artificial intelligence, allowing fully automated infrastructure optimization and autonomous service provisioning. And then also technologies employing extremely precise timing and orchestration of data will transform manufacturing and industrial processes, as well as the networks that serve them. The environment will have this all-inclusive communications over land, sea, air, and space. And then finally, 6G will improve society's ability to respond to and manage emergency situations wherever they arise. So some of the research challenges that we see in 6G, some of these are going to be revolutionary, and some of these are going to be extensions from 5G technology, or begun in 5G and then extending into 6G. Some of these will need to coexist with 5G technologies, and others will just be completely novel research. So here's a short list of research topics as we see them. Probably one of the most basic ones is sub-terahertz research, and then channel modeling and characterization at sub-terahertz frequencies. I guess it should be ultra low latency and time-deterministic processes. And then today, the subject that I'll be talking about, non-terrestrial network design, computing, semiconductor, and optical architectures for terabit per second data transfer, energy efficiency, energy harvesting, batteryless technologies, edge intelligence, artificial intelligence, and increased network security, encryption, and recovery techniques. So where Keysight is at is, so Keysight, if you don't know Keysight, we spun off of Agilent Technologies in 2014, and Agilent spun off of HP in 2000. And HP has been in the sort of the cellular business forever. My first task in the workforce was to evaluate the HP base station emulator from from IS 136 days or 1.5G. And we still have base station emulators in 5G days now. So in terms of Keysight solutions, we span the entire ecosystem from RF interface to the core to the network. And one word before I get into non-terrestrial networks is 6G sub-terahertz research. We have test beds for prototyping and doing R&D for sub-terahertz up to 310 gigahertz, encompassing both the transmit side for signal generation and also signal analysis, waveform creation for 6G PHY research and design. So I'm going to talk a little bit about NTN basics, which stems off of sort of the current work and thought under 5G days. So first of all, non-terrestrial networks for 5G and 6G, it's really there for ubiquitous coverage and ubiquitous communications over mountains, rugged terrains, oceans, plains, et cetera, and again, sort of providing multi-domain communications between air, sea, land, and space. There's always been a need for sort of commercial users to be able to talk when they're on a mountain or over on the seas, but also from a military defense point of view, there's a tremendous advantage in being able to have communications in either denied areas or just where areas have no communications or the communications have been downed. Also from a first responder point of view, also tremendous advantage being able to tend to sort of natural disasters and things like that in forest areas or whatever. Northern Sky Research estimates just tons and tons of money by 2029 for this non-terrestrial networks, which should drive the development of these networks. Now, the 3GPP had already held a study for non-terrestrial networks, and also the European Space Agency also did some of their own sort of outlining of what potential architectures there are for non-terrestrial networks. And so here are the 6 as I understand them. And I'm sure there will be more, and I think as companies get into non-terrestrial networks and developing non-terrestrial networks, that we will see variations on these themes. The first one is the sort of the transparent satellite, where the signal between the UE and the G node B on the air interface will essentially undergoes a form of a frequency conversion, but without changing the payload. So that's why they call it transparent satellite and also bent pipe payload. Then on the second one, this would actually have the signal between the G node B, the satellite would be on the G node B. And so the signal that goes over the interface would then have significant transformation as it goes from the G node B to the core and vice versa. So they call this regenerative satellite. And then also scenarios 3 and 4 insert a relay node there in between for the transparent satellite and the regenerative satellite. And then scenario 5, which I've seen come out of the European Space Agency, is sort of the ORAN version of number 2, which is to say it's a regenerative satellite where the base station has an ORAN instantiation, and the DU is split. The DU would be up in the satellite and the CU would be on the ground. And then number 6 is satellite backhauling, which is to say the link between the base station and the core would go through a satellite link. Now, 3GPP release 17 is basically sort of constraining the problem so as to get something out there to scenario 1, transparent payload, and focused primarily on LEO satellites. Now, officially speaking, non-terrestrial networks means non-ground. So it could be anything that's that's non-ground. So LEO, mid-Earth orbit, geosynchronous, and even HAPS, high altitude platforms, would be a subject of non-terrestrial networks. But 3GPP has decided to just focus on the LEO for now. So in this scenario, you've got the service link on frequency 1 between the UEs and the satellite, and then the feeder link on frequency F2 between the satellite and the base station. So, and then the protocol layers, those would all be transparent, meaning that they would be unchanged. So one of the questions is, how do you account for the Doppler and the delay through the satellite link? So I think the most common method is precompensation, which is to say that you make estimates of the delay and the Doppler through the link, and then you precompensate for it so that the receiver on the other side gets the signal at just about the right frequency and the right time. If you don't do this, there's problems like the near-far problem that everyone's heard of. If things don't arrive at the same time, then they become interference to other transmitters. So it's important for timing to be all synchronized. And for Doppler, on the other hand, your receivers only have a certain frequency range beyond which they would not be able to demodulate the signal. So it's also important to get it within the Doppler, within that range. So how this all happens, first of all, is you have to estimate the Doppler and the delay that happens on the satellite link. So actually, the gateway, the base station, needs to establish a telemetry link with the satellite so that it can, using the onboard GNSS, it can determine the satellite position and speed. And then a new system information block message needs to be transmitted to the UEs that contain that satellite position and velocity. So then the UEs will then be able to read the system information block and acquire that GNSS acquired position and velocity. And then using its own, the UE's own GNSS would then be able to calculate the required precompensation for delay and Doppler. And also on the base station side, it would also have to precompensate so that the UEs get the base station signal at the right time and vice versa. So another important parameter in NTN is HARQ, hybrid automatic retransmission requests. So this is the sort of the do you hear me now? And then how many times or how long do you wait before you give up and say, okay, they didn't hear me? And how many times do you repeat this? That sort of is what's important in HARQ. And this seemed to be fiercely debated in 3GPP. And the debates basically were, so in terrestrial land, there were 16 HARQ processes, 16 times that they could repeat. And the idea here was that for LEO satellites, you needed more than 16 to account for that round trip delay. But there were also parties that said we should disable this. And so, and release 17 has not been completed yet. So they're still in this, but I believe that the decision was kind of like the vaccination thing, where it was like, you could either disable it or you can do 16 or you could do 32, your choice. So they didn't really standardize on that. So for 6G, this is probably another area of research and probably another area of fierce debate. So what I'm going to talk about today in the next few minutes is sort of the software modeling and then implementation with emulators, because we're squarely in the research and development phase here. Again, 3GPP, they're not completed with release 17 yet, so that whole transparent satellite with the LEO, that's not a done deal yet. The protocol has not been finalized. But also all those other scenarios, and then also going through other forms of non-terrestrial, the GEOs and the MEOs, for example, and the HAPS. So squarely, we're in this research and development mode. So what we feel should be undertaken is first sort of going through a software modeling phase. And I'll use the word digital twin here, sort of doing a digital version of what you're going to do in hardware. And then we're going to implement with emulators where possible before you actually build real equipment. Obviously, once you build real equipment and then also do full-scale implementation and also optimization and monitoring, there's more to talk about there. So I won't address those right now. And also security is usually an afterthought and should be planned into the thing as early as possible, really. So digital twin, you know, we've used this word now for a 6G use case. This really isn't what I'm referring to there, you know, sort of going between digital and physical, but more for a sandboxing or kind of a prototyping tool, just to use a computer simulation to do all your 6G work, whether in the PHY layer or with you know, sort of antenna arrays or protocols, or with the environments, doing coexistence studies, for example, or studying dynamic movement, or, you know, Doppler and delay, beamforming, et cetera, et cetera. So a lot of this can be done in the digital domain. Here I'm just showing sort of creating a satellite scenario with dynamic movement, Doppler, delay, and then importing that into a PHY layer design tool that can then help you to assess sort of your demodulation capabilities. Here we're using a 5G signal input, modifying them with the satellite movement and Doppler and delay, and then demodulating. Here you can design your pre-compensation algorithms and et cetera, et cetera. You can also do sort of higher level of simulation where you might actually form a network in the digital twin domain with a UE overhead, and then seeing what all will happen with your simulations here. So lots of things possible in the digital domain. Now, moving forward in the hardware prototyping phase, here I'm showing that transparent satellite, and you can use UE emulators, also G-Node B emulators. By the way, these would have to be modified to be able to withstand a satellite link. For example, all the counters and things like that. Off the shelf, you wouldn't be able to use an off-the-shelf UE or an off-the-shelf G-Node B. So Keysight has begun prototyping sort of firmware that's been modified to do this kind of thing. We can't go in release mode yet because release 17 is still working on the protocol. So we sort of canned in our own protocols here until that time. And then also using channel emulators to mimic that satellite link, and doing this all in the lab, again, for research and development purposes. So here, for example, you might, for 6G research, you might prototype the satellite link and how you might want to do that, what sorts of modulation and demodulation schemes, researching HARQ, for example, researching pre-compensation algorithms. So doing this kind of a lab test, you can test the key PHY layer aspects of non-terrestrial communications like Doppler shift, delay, HARQ, and in 6G modulations as well. And entirely using COTS off-the-shelf equipment. So So we did this in the lab and actually prototyped some NTN results, applying the channels to our G-Node-B emulator and our UE emulator. And we're able to show the effectiveness of our precompensation in that before precompensation, we had pretty bad constellation plots and high error vector magnitude, and then with compensation applied for Doppler, cleared up the constellations and lowered the error vector magnitude. And that was for Doppler. This is also for time delay, same thing. And also we could examine the throughput and the block error rate. And then also HARQ extensions, we could also research HARQ. Again, not to discount anyone else's research, but just to show that we have a test bed for doing HARQ. And there are other considerations besides throughput. So no offense to anybody here who said anything else about that. Wanted to just quickly show the DU-CU split scenario where we can mimic that with basically our ORAN test tools. We have a DU simulator and a CU simulator. We can connect those up, and then you can build your own FPGA-based modulation and demodulation with some of our tools. And also same thing with the backhaul. With the backhaul, we have a RAN simulator and a core network simulator. And then in between, you would insert this sort of the simulated satellite link. Again, from a research perspective, you can build your own modulation and demodulation schemes. So with that, we're proposing here software models and also hardware test beds for 6G NTN research, and you can customize your scenarios in software and hardware and do modeling and emulation for HAPS, and not just LEO, but NEO and GEO as well, and a variety of software and hardware test tools. So with that, I'll take your questions.
Thank you. Any questions for the room before we go to chat? All right, I'll read one for chat while you're thinking. All right, so the first one, let's see. Wow, there's lots of questions coming in here. We'll go with this one. Okay, so how will device-controlled reference signal work with NTN versus 5G, or will we still continue with network-controlled references and SIB exchanges?
Yeah, I think in large part it won't change, but obviously the protocol is changing and they're working on that right now. How much change there will be, I think, is dependent on the NTN scenario that's being implemented. And so that's why some of those scenarios had relay nodes in there. The relay nodes, I mean, obviously, I don't know what they are. They could be on the ground. They could be UAVs. So I think that was an attempt to try to preserve as much in the UE as possible, although I still contend that timers and counters and things need to change anyway, but maybe those are easy to change. Yeah. Okay,
we've got two other questions. The next is, what's your take on reflectors and its use in vehicle V2V and satellite LEO for autonomous vehicles, trains, etc.?
Reflectors. I'm not sure what reflectors are.
Oh.
And V2V, sorry, the question was about V2V as well.
Yeah.
And how that relates to NTN.
How that relates to things like autonomous vehicles, like trains and cars and things like that.
Bob's my colleague. You want to take that? Use a mic. Yeah. Bob's also from Keysight.
Can you hear me?
Yeah.
Okay. Yeah. So in terms of, let's see, the question was related to reflectors, and what was the other part?
And V2V with
V2V.
NTN.
Okay. So for both of those, for the reflectors, the fader that Raymond was showing up there, and the channel modeling that we can do with our channel modeling tools, you could set up reflectors in the environment, and so you could do beamforming and model different complex reflector schemes to leverage, different reflectors. And with the system view tool, you could have materials-based real-world models for those things to increase the fidelity of the model. Similar story with V2X, vehicle-to-vehicle kind of communication. We have links there where we can simulate different paths and things of that sort in the emulator and in the digital twin software. So if you have more questions, we could follow up.
Awesome. I'll take one last question from the chat. Given we as researchers and as a standardization body, in your opinion, how do we move security into the design phase versus that of an after-the-fact approach?
That's a great question. Yeah, probably if we answered that question, then everything would go better. I don't know, probably just a will to do it. I know like if you take ORAN, for example, it was kind of like they built the house first, started working on ORAN and then formed the ORAN security group. So yeah, I think it's just a will to do that. Yeah.
Thank you.